In this video, we'll look at the Delaunay triangulation problem. We motivate the problem using the following example. Assume we have a train, and we have measured the height of this train at a particular point. For example, the height of this point is measured to be 5 meters, and etc. Now the question is, given the location of users, how can we estimate the height of the train at this location? Of course, since we have not recorded the height of the point Q, we have to estimate it using the nearby points. But which nearby points to use to estimate the height of Q? One way to do it is to do a triangulation first. First we triangulate this set of points, and now we look at a triangle that contains a point Q. We assume that the terrain in this part of the region is flat, so therefore we could estimate the height of Q using a linear interpolation of the heights of the 3 points that form the triangle containing it. One issue here is how to do this triangulation, because obviously there are more than one way to triangulate the set of points. When we look at these two different ways of triangulating, you could see that the top one is much more desirable. The main reason for this is that all the triangles in these examples are fat. In other words, they don't have narrow or small angles, whereas some of the triangles in this picture have very narrow angles. The reason this is a problem is because remember that our linear interpretation requires the assumption that the region must be flat inside a triangle. So clearly, if I sample lots of dense points from the train, in other words, if I measure lots of heights, and if all my triangles in the triangulation are flat, it is kind of reasonable to assume that the terrain in this region will be flat. Whereas if my triangles are long and skinny, it is unreasonable to assume that this part of the train will be all flat. Because of this, in many applications that require triangulation, it is much more desirable to have a triangulation that avoids having triangles with the small angles. So to formulate this mathematically, we could create the following sequence of angles. So given a triangulation, we would sort the angles in increasing order. Alpha 1 would be the smallest angle, and alpha k would be the largest angle. We could say that a triangulation is better than the other triangulation if the smallest angle of this triangulation is better than the smallest angle of this triangulation. If their smallest angles are the same, then we look at the second smallest angle, and so on. We say a triangulation is angle optimal if it's a maximum in this order of sequences. In other words, its smallest angle is the largest, then the second smallest angle is largest, and etc. One technicality that we need to deal with is that what if some triangulation has fewer angles than some other triangulations, and how do we compare two lists where one has fewer elements? It turns out that this is not a problem because all the triangulation have exactly the same number of triangles, which means all the triangulation have exactly the same number of angles in them. The number of triangles in the triangulation is 2 times n minus 2 minus k, where k is the number of edges on the convex hull.